Welcome everybody, you're watching Mr. Fugu Data Science. Today will be an explanation of the logistic regression. Thank you to the recent subscribers and viewers. I greatly appreciate it. Don't forget to hit me up on Instagram, Twitter, and if you can, please help support this channel and buy me a coffee. Let's get into this. Here's the imports you're going to need. It's going to be fairly simple. Let's give a basic background and clarification. Logistic regression is used for classification. We showed in the previous video the ham and spam SMS messages for our sklearn module 1, which will be located on my GitHub with a link in the description below. Basically, what you're trying to do is estimate the probabilities for some instance belonging to a particular class. Using logistic regression, you're preserving the marginal probabilities. You're also using the coefficients to aid you in detecting what input variables are important. And you would say to yourself, why not use linear regression? In order to use linear regression, we would have to create a threshold for our classification. In this problem, we are using a pass-fail. The issue with linear regression is you have unbounded results, meaning that we're not receiving a 0 to 1 output. So what does that mean? Well, you either have values that could be greater than 1 or less than 0. And the other issue that you have when you're plotting linear regression are outliers. Those can dramatically affect your best fit line. That's something that we want to avoid because it increases your error. What are some differences from linear and logistic regression? Linear regression fits a line to the points of data which can be used to estimate or predict a new value. Logistic regression fits a line to best separate between classes. We can connect linear regression to logistic regression. We're taking the labels and finding a predicted label and output a probability. So we have our original label and we would like to predict it here with this y hat, meaning that it will be our predicted label. And using the sigma function, which will be shown below, we could take the linear regression model and conform to the range of 0 and 1. We would do this by taking the predicted value and using the sigma function and plugging in our linear regression, allowing us to make predictions for a probability in the range of 0 to 1. You can equate this as the distribution perpendicular to the line for our decision boundary. This means that the points residing in our plot are separated by a decision boundary. The points will be separated by a distance parallel to that line. Think of if you're doing error checking, and that distance is therefore giving a probability for that class or not. The farther they are from that line, from the decision boundary, the higher the probability for that class. For instance, if we had this line here, and this was the function that we were estimating, and these were the classes that we were separating with our decision boundary, this red line, this distance here that you notice will dictate the probability. The further this line is from this decision boundary, the higher your probability is that you are within this particular class. What are we trying to find with our parameters, our coefficients? For instance, I will use the notation of beta, and you are using one of two methods to estimate these. If we are using the linear approach, we would use least squares. There's an approach called iterative form of least squares that can be done, and there's the max likelihood estimation. But what are we exactly trying to calculate with the logistic regression? You're trying to compute a weighted sum of the input features plus a bias, your intercept term. There is one coefficient per input. We're going to use the max likelihood today. So starting with the linear regression, we're going to have our hypothesis as our f of xi, representing the predicted response for some observation. So we're going to say capital X, which could be capital Y bar. You may see that notation, or like this. And we're saying the probability that this occurs. So you're looking at this point, the output will be a real value, not a label. So what you're doing is you're throwing in some labels, finding out what the output will be, which is a probability. You're not outputting 0 or 1, you're getting an actual number. So in order to mess with this, we need to use the logistic function or the sigmoid, which is this. Now pay attention here, right here. That's going to be dictated by however many parameters you have, okay? Here's the plot of the sigmoid function from 0 to 1 with a boundary right here of 0.5. If we were in this range right here above that, we'd be in this particular class. If we were anything lower than this line, we'd be in this particular class. understand that the logistic function, the sigmoid function, is basically a class or a family of functions. Remember that if we're manipulating, if you look right here, we're manipulating the parameters, and that's going to cause the shifting of this plot. We're trying to maximize the values for this to give us the best fit line. You could think of it like that. What we would like to fit is, say we have some data relative to gender, which is on the y-axis, and weight, and here's our values. And we would like to distinguish based on these values what is a male and what is a female. When you're getting these probability predictions, you're basing it off of y equals 1, so a true value, okay? So whatever your true value is. We could say that this is a male for our true value, whatever. But that's what it looks like. And basically we would like to try to find some kind of function that would come in here and work best to describe our data. But in order to do that, we need to find the parameters. So to start by finding what's called the log odds. Think of when you were doing your intro to statistics, you would have seen something with gambling with your win-loss ratio. And that's what's going on here. And we need to convert that into a log odds. The log odds is good for a lot of reasons. When you're manipulating logs, it's always more convenient to work with addition operations than multiplications. We need to equate this left-hand side here to this log odds, which equals now our parameters on the right-hand side. To get rid of this, you got to just take the exponential, and we'll have to do some manipulation for this. But this look at, feel free to pause this if you want to see the plotting. But here's our log odds, all right? So what you notice is at this particular value of 6 for our odds, it prints out 1.79. It's really close here, but that's the actual value. 1.79 as a log odds. But what does that tell me? It doesn't tell me a probability. Well, wait, we can manipulate this and understand this y-axis here. It's denoting that you're taking the natural log of whatever x value from this. And how do we interpret this? If we're taking the log right here, if we're taking the log of x, when the odds equals 6, it returns 1.79. When we take the probability, we would say, let's get that log odds and plug it in to our sigmoid function, and it returns a probability of 0.86. If the probability indeed were 7, let's find the odds ratio. Finding the odds ratio, we would do probability divided by 1 minus the probability. Probability of it happening divided by the probability of it not happening. And that'll give you 2.3, meaning you have a 2.3 to 1 chance of whatever occurring. Okay? That's what's going on with your odds ratio. Moving on from the log odds, understand that logistic regression, the dependent variable is called the logit, okay? And that's what this is here. Therefore, the odds is a function of the probability of getting a 1. Now, how can we clarify this with an example? Let's say that we have, among men 40 years old, the odds of acting weird before the age of 50 are 2 times greater for never married men. This is to be funny, all right? So pay attention. I'm saying never married men. So we would say that the odds of being weird given never married divided by the odds of being weird for someone who is married equals 2. We could say that the odds of being weird given never married over the odds of being weird equals this. Pay attention in particular what parameters you're printing out, because for someone who's never married, and we'll give that as class 1, this right here is what it looks like for us to have our parameters being 1, and this is what it looks like for being 0. And so therefore we can increase our x by 1 unit, which would mean that the odds, which is the exponential of our parameter, is multiplied by 1 with all other independent variables held constant. Before we go further, like I mentioned before, this mentioned here we have our sums. Linear regression, we would be working here, and logistic regression, we're working here. Let's look at an example. Let's say that we're given 0.789 for our b of j, and let's assume that our x of j equals 1. Then we wind up with a value of 2.201. What does that even mean? We would end up with each value odds for our response variable e of j being true. So any increase or decrease for our value of j would increase 1 unit. So if you were using x of j as some value such as months, years, whatever, some kind of interval for x, you will end up doubling the odds of your response being true, with all other items being constant. If you were dealing with some kind of categories rich and poor, which would be encoded like this, we would say you have a twice as likely chance of being true for someone who is rich. Now we have to do some manipulations from what we started with before here, all right? We have to manipulate to get our probability by itself. We need to do some substitution, move everything over, combine everything, divide through, and equate to 1. From there, we will equate to 1, pull it outside, do some canceling, and here's what we end up with, okay? So far, if the logs are linearly related to the capital X, then the relation between X and P are nonlinear. Then you will have that S-curve that we had for our logistic function, which is here. The decision boundary will be based off of your beta plus the beta X equaling 0 will be the solution to the separating line for the predicted classes. The distance between those lines is this right here. Logistic regression will tell you the boundary is between classes as well as the dependence of the class probability boundaries. If you download this code, I have a great number of links for tutorials, derivations, everything. I highly suggest you download this. We're trying to do a separation for the boundary for classifying. The likelihood estimation will be maximized so we can get the best separation between classes, such as an example like this. Understand that the properties of the decision boundary are generated from the hypothesis, not the data set. We create this hypothesis suggesting that our data form this kind of function. These are the parameters. For instance, these may be the parameters that we find that work out to something like this. And so then there you would say that your parameters fall within this range. The decision boundary has some particular behavior. Ideally, you would want to aim for your recall and precision to be 1. If you had low recall and high precision, you would have a situation where you would want to reduce the number of false positives without adjusting false negatives. You will choose a value which will either retrieve a high recall or a low precision. This would occur in situations where you would have, for instance, advertising. You would want to make it clear and have a positive impression on the viewer. If you were in a situation with low precision, high recall, think of falsely labeling someone with cancer as not having cancer. So important to understand, all right, that we are trying to find our parameters in order to create that decision boundary. That is for the next steps for us. We want the best predicted weights such that the probability of X will be as close as possible to the label. To get the weights, we can do a log likelihood estimation to maximize this. Logistic regression predicts the probabilities and not just the classes. We're going to need to set up some Bernoulli trials, which after you perform the trials sets up binomial distribution. We have this right here where the x of I is our vector features and the y is our classes, where p equals 1 is true and 1 minus p is the probability of not being true. Here's the likelihood right here with the Bernoulli trials. This same thing, we're just multiplying all of our entries that we have. The likelihood is the conditional probability of getting the values we observed as a function of your parameters beta. You're given some label y, which is a function of the parameters beta here. Now let's look at this example. Given some class 0 or 1 for your label, let's look at the probability for y hat. I'm giving my label as 1. I have an 80% probability of this occurring. My likelihood is 80%. I have some label of 1, my probability of 0.1, likelihood of 0.1. You get the drift, right? But label of 0, probability of 10, likelihood of 90%. Label of 0, probability 80%, likelihood 20%. We want to maximize this log likelihood with respect to our parameters beta. As a side note, using sums versus multiplications is easier to calculate and compute for your computer. Always remember that. There are benefits with plotting and concavity with using the log and reaching a max. We separate from above, which was with the multiplication, now using the log so we can get our additions. From there, we have to split this up on this portion here. Then we're going to do some manipulating so we can get it back in the form of our log odds, which you'll notice here. And then we still have our 1 minus probability, just like a log of it not happening. Now, we're going to do some substitution for our betas here for every spotlight you're going to see with the probability of X, okay? Then you have to pay attention to the sign down here. You got to pay attention to the sign that comes out here. Now, another thing, when you're maximizing this, you're going to end up pulling out and doing a negative, and you'll see that when you get your results if you're playing around. So if you're trying to train your data This is where the cost function comes into play, and it aims to estimate our parameters beta. And since the log function estimates the max, we want to actually find the minimum now. And don't forget to put that negative in front. So think of it like this. If we have some label, we would like to say, what's the probability of getting this label? 1 with a negative log of the probability. And here's the probability of this not occurring. So let's look at what is occurring here with our negative log of our hypothesis and then negative log 1 minus that. We have this division because we're interested in going from 0 to 1 for our probabilities. All right. So let's scroll down and look at each one of these separate. First is the negative log of our hypothesis. You'll notice for our cost function for the label equaling 1, here's our cost on the y-axis, here's our h of x, and we're saying if we have a cost of 0, then we will say let our hypothesis of being the label and actually predicting the label are the same, and we have 0 cost. If the label is 1, we predict 0, we're going to incur a high cost. That's what's going on here, and it explodes. Therefore, your probability is 0 if you predict your label of being 0 when the label should have been 1. Let's look at this the other way. If the label is 0, we predict it being 0, we incur 0 cost here. The reverse, if we predict it being 1, the cost becomes quite high, and the label was 0. Now what happens? Well, we have that log likelihood function, but we like to maximize this. But unfortunately, we're unable to do this, and you can't directly use derivatives with respect to the parameters. You have to use approximation methods, such as gradient descent, Newton-Raphson method, other iterative approaches, cross-entropy, etc., etc. We want to use the optimization of the cost function to do this. For instance, I'm going to use gradient descent. I'm going to show Newton-Raphson because most people show gradient descent. But gradient descent can have some issues. You have to worry about getting stuck in a local minima with nonlinear functions, and you have to choose your step size. Now, Newton-Raphson is interesting. 1, you have to choose a starting point. 2, it's using root finding. All right, that's different than what's going on with the gradient descent. Since we can't use the derivative and set it to 0, let's get on with this. Let's take our log likelihood from above and use the Newton-Raphson method here, where we're taking our starting point, which is this beta I, which is a point that you arbitrarily pick in the beginning. One note, you should try to pick this close enough to the minimum position for your function to have success. I'll mention more on that later. Then you're going to take the first and the second derivative of your function with respect to beta. We'll take the first partial derivatives with respect to the parameters, which is happening here. Then you have to do a little bit of substitution and combine the terms and bring everything out. You need to perform the second derivative with respect to your parameters and combine everything. You're only looking at the first iteration here, and I suggested generalizing the first and the second partial derivative so you can see what's going on, and you end up with something like this. And this is what would help you find your parameters for your particular function. And you just have to iterate through this, through your data. I left quite a bit of examples for you to look at derivations and everything like this if you need to go further. We're working right now in the 1D situation with one iteration. If you want to go into multiple dimensions, here's a lot of text that can get you further. And here's the basic gist of it. You still have the same situation, right? But in order to go into multiple dimensions, you have to use Taylor expansion, gradients, and the Hessian. This example here, which I wanted to distinguish, will go from your point of interest that you start with, beta naught, and then it will take this piece right here where you're basically using a line from the point of interest you started, which would be tangent to the curve. The line where it crosses the axis will then be used as your new starting point, okay? This uses a function to try to map through and find your roots, okay? Instead of using a line which is tangent, it'll use your function, which is like, think of like using a parabola, and at each minima for it, that'll be your new location for you to move over. Newton-Raphson's very interesting because it takes very few iterations to find your parameters. Okay, if you're confused, pause the video and look at this highlighted part right here. But basically, in the end, for the multidimensional part, it'll look the same, but this is what you're doing. You have to remember what's going on with positive definite matrices for the Hessian and complications when that doesn't arise. But here's your inverted Hessian and your gradient. This is how you would solve it in multiple dimensions. I left links above so you can go to the math and there's derivations, but they're not extensive. So let's look at the first part where we're iterating through the Newton-Raphson method using the tangent lines. I know the lines aren't straight, I drew it, I freehanded it. But if we started with this first line x naught, which would come down to some point that we initiated at, it would cross the axis here. Let's say this is x11. This is the new starting point that we're going to use for our new tangent line. These purple lines right here are denoting where our roots are that we're trying to get to. The good thing about Newton-Raphson is it has a division by zero exception, so you can basically know when to stop or when you found your roots. And here's the alternate way that I mentioned before with using the quadratics. Now, let's think about a few things. The parameters that you just found are placed back into your equation and used to find your probabilities. What's the takeaway from all of this? At each iteration, you approach a minimum for your cost function. You are trying to find the best fit. The parameters that are found will be those. Take those parameters, put them back in your function, and you will be able to best estimate your given data. You can make predictions based on the parameters using your data and find out how well your actual data measure against your prediction by accuracy, recall, precision, etc. Suppose I took the data I formed in the beginning with the height versus gender, and here's our labels, and I'm using something interesting here if you've never seen this before. What I'm doing is needing to convert this. I run it through my logic, I fit it with the Newton method, I find my parameters, and I show my prediction, and here's my predictions after 8 iterations. This isn't what you think it is for accuracy, so don't get that confused. Pay attention to these because we're going to come back and find out how you get these. So we're going to take our data that we have and we're going to take those parameters we found above, which are here. And I'm going to plug in each one of my points that I iterate through. And I store that as my log odds. Then I run an exponential on this. This is now my function, okay? So I plug this back and this is my function creating these. I run the exponential and now I get my odds. I take those odds, all right? I take my odds and now I put that in the numerator and then I go in the denominator and do 1 plus that. And that gives me my predicted probability back. This is showing you what's going on intuitively, okay? So please pause this and look at what's going on. This is creating my log odds. I take the exponential, I return the odds. I do the same thing, but I take the odds divided by 1 plus the odds, return the probabilities for each one of my item. Here's my log odds, here's my odds, here's my probability returned, which match what I did for my model through the stats module. You can take the confusion matrix, take both of the positive values, okay, which are these corners, add those up, that's going to be 90% accuracy. Run this through sklearn, you don't get the same items back, okay, for your intercept and your beta coefficient, because I'm thinking that this is running a regularization term in the background that I don't know about. You can do what people usually do is like a C equals and then some crazy big number that you're plugging in here, but I'm not going to work my way backwards. I'm just going to show you sklearn, here's your coefficients, your intercept. Here's your predicted value. Here's the actual value. It's saying I have a 50% accuracy. I would have 0 plus 6, which will equal about a 60% accuracy for this model. Gradient descent versus Newton-Raphson. Finding roots converges quickly. When the second derivative is known, it computes quickly, such as logistic regression. You got to provide a starting point, which is very critical. The runtime is pretty crazy. The memory used isn't very good. Computationally intensive, but since you have low iterations, it converges quickly, if it converges, and it's faster than the gradient descent, even though it has poor runtime and memory. It supersedes the number of iterations. That's why it's performed. The second derivative helps you converge because it is used for each step. Very large data sets can be a problem computing Hessian matrix, but to get around this, you may decide to decrease the complexity or dimensions, but result in more iterations. That's your trade-off. Paying attention to the Hessian matrix is important as well. Make sure positive definite. When using sklearn, pay attention to your solvers, such as LBFGS for low memory something. Gradient descent finds the min and max of the first derivative. Can be troublesome finding the local min and max. Can be combated by using a random approach. Okay? Parametric, we need to adjust hypertuning. The runtime isn't too bad, n times p, and the memory is just linear. solvers over gradient descent for choices. These three right here, the pros. You don't need to pick a parameter for your learning rate. Usually runs faster due to less iterations, can work out gradient, but there are some hiccups. The cons, complex and seems like a black box if you don't know what's going on, so do some digging. Pros and cons with logistic regression. Good because it classifies and returns a probability. You're also able to determine the relevance of a predictor by its sign and size, which is good for interpreting and training. The cons, you can have overfitting with large data sets, so you would need to use a regularization term, or at least consider it. Perfect separation is a problem if two classes could be completely separated. Therefore, you shouldn't use machine learning for this situation. But adding a penalized term to the weights or probabilities would be suggested. Now, I'd like to say, if you combine gradient descent with Newton-Raphson, you could have some success where in the first steps, before you get relatively close or to the minima, run the gradient descent. Then when you're getting reasonably close, use Newton-Raphson so you can approach extremely quickly, because the last few steps of getting close in gradient descent can seem like forever because it could take a great deal of work to get there. Therefore, using the combined Newton-Raphson would help you immensely. But as always, please like, share, and subscribe. And I hope this brought utility to someone. Hit me up on Instagram or Twitter. And if you can and felt that this was useful, help support the channel and buy me a coffee. Have a good one. Bye.